So, the last few lectures we learnt about different types of data structures. We talked about lists, then we talked about trees, then we did specifically binary trees, binary search trees, and priority queues. This is what we had studied. Now, if you look at all these kinds of data structures that we have studied, whether it is a list, whether a tree, binary search tree, or a priority queue, we always had some kind of a node which had kind of a higher priority. There was a header node in the case of lists, which then pointed to other nodes. Does not matter whatever the implementation, array, or we put in a hierarchy there. For a tree, for example, we said there is a root, and then there are children, and so on. Similarly, for a binary tree, we had what is called a left child and right child, and we had a node that was designated as the root. Now, let us think of another problem. Today with the all of you are on Facebook, I am sure, and when you look at Facebook, what are you doing? You have a set of friends, and so a set of friends watch you, and then you watch somebody else, and so on. You are connected to somebody else who is also having a set of friends. You also watch them, and so on. Now, in such an example, and this one has perhaps another set of friends, some of them may be disjoint with respect to you. Let us say this is you, this is your friend 1, friend 2, and so on. Okay. So, what is interesting is this is called a social network, and interestingly this social network has a lot of branches, and in the social network there is nothing like in your friend circle, for example, you have some ex friends, and amongst these ex friends one of your ex friends has another set of friends who are disjoint with you. It is possible, and there is nothing like a hierarchy. In the earlier data structures that we saw the header node, then we saw the root node, and we said access to any other node is via the root node here, via the header node in the list and all that. Here on the other hand, there is no hierarchy amongst the nodes. Okay. So, we want to represent something like this. This is a very, very common natural phenomena in nature, where generally things can be represented such that there are different nodes, each one has its functionality and they are connected to each other by some property. Then to represent something like this, for example, I may want to find out who are all the friends that are connected to you, or I may want to find all the friends who are connected to F1 or F2 or F3 for that matter. Then if I was using a tree, then I would say if you were the root, then I would say to access any of your friends I have to go through only you. Then what happens? People who are not friends of you, I cannot get access to them. So, another nice type of a data structure is what is called a graph. A graph is essentially consists of a set of vertices. The vertices here are you and your friends in the social network, and these vertices are connected by arcs if there is some connection over here. So, you have a set of vertices, and if there is a connection between the two of them, something you are a friend or whatever it may be, then that is represented by an arc. The vertices are also called nodes or points, the arcs are also called edges, and edges may be, for example, you may think for example that F1 is your best friend, but F1 does not think that you are his or her best friend. So, the graph, for example, when I am looking at it over here, I might have, if I am looking at only best friends, you think F1 is your best friend, but F1 thinks F2 is his best friend, and so on. Okay, it is possible something like this, and F3 perhaps thinks you are his best friend, but you do not feel the same way. Okay. Such graphs are what we call directed graphs. You can have directed graphs, or you can have undirected graphs. For example, if I am looking at network communication across, how do you connect to various websites, then you are sitting at your home with your computer over here, then you are connected to, let us say if you are using BSNL, you are connected to a BSNL router, then this BSNL router goes through number of various links through the internet, and perhaps your server is somewhere found over here. Okay? And normally these links are what we call bidirectional links, and then we say that this is an undirected graph. Both the graphs are important in practice. We like to analyze both of these graphs. Okay? So, basically what is it that this defines whether a graph is directed or undirected? The edges may be directed or undirected. When the edges are directed, the graph is called a directed graph, otherwise the graph is called an undirected graph. Now, how do you define an arc or an edge? We represent it as an ordered pair of vertices. See the example over here. If there are n vertices in the graph V1 to Vn, if there is an edge between V1 to V3, let us say, we represent it by a symbol like this, or if you are writing it, you would put it as an ordered pair, okay, U comma V, all right, V1 comma V2 in this particular example. There is an edge between V1 and V3, you write it as an ordered pair like this, all right. Now, then you also have what are called, so if you want to define a path, how do I define a path? If I want to find a path from here to here, then let us say this is node V1, V2, V3, then I would say my path is from V1 to V2 to, and V2 to V3 is my path. So, this corresponds to a path. Okay. So, you can have a set of sequence of vertices which gives you the path. So, that means what am I saying here? I can represent it this as V1, V2, V3 corresponds to a path. That means there is an edge from V1 to V2, V2 to V3, and that represents the path starting from here to reach this particular node. Okay. Now, you can have both labeled and unlabeled graphs, but labeled graphs are what we are going to look at. So, when I look at a labeled graph, I have something like this. Vertices are labeled here. Say here, let us say, and if I have weights on this 4, 6, 8, 9. So, both edges and nodes can be labeled. There are nodes and there are edges can be labeled. What do these weights mean? To give you an idea, if you want to, let us say, travel from one place to another, and then this weight could correspond to the amount of time it takes for you to reach from point A to point B for that matter. So, this is what a label graph is. Now, I want to just leave you with one example, although we will not be discussing this. Graph problems can be found in various applications. Here is a very, very interesting example. Let us see this. Let us say now here is a graph where I want to, this is a 5-point intersection. There are 5 lanes which are intersecting over here. There one road is called A, another road is called B, C, D and E. C and E are one way, A, B, D are bidirectional roads. Now, I want to, let us say, my job is to design a traffic signal for this. I want to put a traffic signal such that no accidents happen if you follow the signaling rules. So, how do I go about defining it? Okay. Of course, first thing, let us assume that this is India and all left turns are free for the time being. We will assume that. Therefore, B to C is permitted. Similarly, A to B is permitted and E to A is permitted. Okay. And D to is of course is a right turn is not permitted, okay, without a signal. So, we will assume. So, what we will do is, I want you to just see what I have done here. I have converted this problem of designing a traffic signal for this such that I have converted it to a graph problem. What have I done over here? I have basically enumerated all the possible paths that exist. That is, I can go from D to B, I can go from A to C, I can go from E to C, I can go from A to D, we can go from D to A, D to B and so on. So, what do? I look at all the paths that all the roads that can be reached from A, from A I can go to B, from A I can go to C, and A I can go to D. So, I make them as nodes. Okay. Similarly, from B, what are the paths that I can take? I can go from B to A, I can go from B to C, and I can also go from B to D. So, there are 3 paths again. Similarly, I do it for the rest also. D to, I have D to A, D to B, and D to C, and E to A. From E to, I have E to A, E to B, E to C, and E to D. All the 4 paths are possible. Then once so basically what is it? What are the nodes? The nodes of this graph correspond to the the paths that are possible. If I am traveling on this road, and if I am taking a vehicle, which are all the legal paths that are allowed. Now, my job is to design a traffic signal. Then what I do is, I join a pair of nodes by an edge if both of them cannot happen simultaneously. So, let us look at this. Let us look at A to D and AD and let us say AD and let us say that I am looking at AC, AD and DB. Okay. So, this is AD and this is DB. Remember, this is left turn, right, left handed traffic. So, this is going this way and this is coming this way. So, both of them cannot happen simultaneously. So, what I do is I connect here, this may be a little incomplete, but what I have done is I have connected all the nodes in this graph which cannot happen simultaneously by an edge. Okay. Then what happens is this becomes what is called, now as I said I want to define a traffic signal. So, what is the problem of traffic signal now? Basically, it is a question of colors. What are the colors that you are familiar with? You have green, yellow and red, or green and red for the time being, let us say that. So, what this means is that when I am defining colors for this, 2 paths which intersect cannot have green at the same time. Okay. So, what I essentially do is I try to find out how many different colors are required to design this traffic signal. Okay. How do I find the number of colors? So, what happens is it is very interesting that designing the traffic signal for this intersection simply becomes a problem of finding a graph, edges in the graph, and ensuring that 2 nodes which are adjacent to each other, that is 2 nodes which are connected by an edge, do not have the same color. Okay. So, first for example, so A in this example if you see A, B, C, E, A simply does not matter at all. You do not have to have any color for them because you do not have any edges, they are completely free left turns. A, C if I color as green, then B and B A and B D cannot have the same color. Okay. So, you do this kind of then you basically if I given, then you find out what are all the colors that A, C can go with, what are all the turns that A and C can happen together. For example, if I am going from I can go from A to C, and I can of course make a DC. There is no I can make a free left turn from B to C. So, these two do not intersect. So, it need not have to have the same color. So, basically what you do is you look at this particular graph, start off with coloring this, give a different color to this, okay, and similarly you keep doing this until you have satisfied all of them. Okay. So, you find until all the nodes in the graph are colored. So, this is just an example. Coloring problem is a difficult problem. In fact, finding the minimum number of colors is not a simple solution, but this is just to illustrate that you start finding graph kind of problems even for something like this. You will not even think about it. It is an intersection that you want to design, and for this intersection you can convert it to a graph problem, and then it simply boils down to a question of not giving 2 adjacent nodes the same color. Developing the algorithm for this problem is a little tough. It is a little beyond the scope of this course, but to just give you an idea. Now, how do you represent graphs now? Graphs can be represented by matrices. Here is a graph, and what it tells me is whenever the this is what is called an adjacency matrix. This is a two-dimensional matrix where you have vertices on the y axis and also on the x axis, and if between a pair of nodes there is a edge, you mark it as 1, otherwise 0. If this is an unweighted graph, if it is a weighted graph, that is, if it has numbers on the edges, then you put that number over here. There is another representation called the adjacency list representation. The adjacency list representation, for every node, it is an array of nodes, and at every node you have a linked list which says to which node it is connected to. For example, A has edges to B and D, okay, and B has edges to A, C, D, okay, and so on. Okay, put all of, for every node you give the, since this is an undirected graph, we also show that D has edges to A, B and D, because both the forward and the backward edges are present. That is what we assume it to be. Okay. So, these are two different representations of graphs. So, now we have, I think I have motivated you sufficiently to look at graph problems, and what we will do is in the next 1 or 2 lectures, we will look at some different problems on graphs, and so we will stop with this introduction on graphs now.